Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Everyone watching this video is a fan of spaceflight. The modern use of the word fan is synonymous with the words enthusiast and aficionado, someone who exhibits a strong interest or admiration for something, or somebody. This is a milder meaning than the origin of the word fan itself, which is short for fanatic. A fanatic is someone who exhibits uncritical zeal or an obsessive enthusiasm. This is an important distinction. While it is good to be a fan, we should avoid being a fanatic. We need to be critical of our ideas and beliefs. Only by putting them through the crucible of critical evaluation can we be sure we are approaching the truth. Science should never assume a conclusion. It should collect and evaluate evidence, and develop theories based on the weight of that evidence. Science should never believe that it has the absolute truth on anything, just that the current evidence supports a theory, and science must always be willing to change its mind if the evidence shifts. This is contrary to how the human mind works. Humans prefer certainty and absoluteness over the risk of being wrong. We tend to fear and dread the unknown or the uncertain. Admitting that they leave room for doubt of their own theories leaves scientists open to attack by those who claim absolute knowledge of a subject. And this brings us to a quandary. We must enthusiastically support the space industry without falling into uncritical or obsessive behavior patterns. We avoid this by listening with an open mind to constructive criticism of our ideas. In science, this is called the peer review process. Your peers, those with knowledge of the subject matter, review your findings and look for things that you might have missed or gotten wrong. So it is important, when trying to define reality, to get many viewpoints, even contrary ones. This introduces us to the concept of advocatus diaboli, or devil's advocate. This was once an official position in the Catholic Church. This official had the duty of making a strong argument against a candidate for promotion in the church or canonization into sainthood. It was this official's job to uncover any character flaws or false information presented to the church. The job did not require the advocate to believe what they were arguing, just that they raise relevant objections for consideration. This adversarial process is critical to an objective search for the truth. And this brings us to the second problem. An objective evaluation of our ideas can devolve into destructive criticism. Destructive criticism sets out with the goal of destroying not just your position, but you. I will often watch YouTube channels that are critical of Elon Musk or the Starship concept. Many of these channels are moderated by learned people in some aspect of the space industry. These people will often decry the cult of personality that has built up around Elon, and accuse him of being a charlatan or con artist. You will then see them attack his supporters for showing condescension toward the old space industry, or for using derisive arguments. Then they will use those exact same techniques and arguments, being condescending and making personal attacks against the fans of SpaceX. These attacks are not limited to one party or industry. The right attacked the Obama administration for supporting Tesla with a government loan. Mitt Romney called Tesla a loser. The left attacks Elon himself for being wealthy or unconventional, for not paying homage to the old way of doing things. His accomplishments are ignored. Tesla was not even invited to the White House Electric Vehicle Summit, despite being not just the world leader in this sector, but a 100% American car company. Tesla is, in fact, the first successful new car company in America to produce over 7,000 cars per week since Chrysler was founded in 1925. And criticism isn't targeted just at the company. Attacks on Elon himself have become very popular lately, and any flaw is trumpeted. They could save themselves time. Elon Musk is a deeply flawed human being, but I think his detractors are confusing him for someone like Trevor Milton. Trevor Milton took over a natural gas-powered truck startup and founded Nikola Motors. He promised higher efficiency and then hydrogen power. Hydrogen power is awesome and green when you have a green way of making hydrogen. Right now we don't. Solar-powered electrolysis is a possibility, but putting that electricity directly into a battery is almost always more efficient. Trevor was a convincing speaker, and I can't say at this point if he believed what he was saying, or knew that he was misleading his investors completely. There is a fine line between promotion and propaganda. Though towing a truck to the top of a hill and letting it coast down, claiming it's driving itself, is certainly going to get him into some trouble. But ad hominem attacks, while dismissed by objective evaluators, are dangerous. They can be a prelude to something much worse. Throughout history, extremes of both the left and the right become almost indistinguishable in their effect on humanity. It has been said that politics is war by other means, and we are seeing the power of politics brought to bear against Elon Musk and his companies. To ignore these trends is to ignore what is almost certainly the greatest danger to the advancement of humanity. I support Elon Musk not for who he is, but for what he has done, and what he is trying to do. I have loved space science my entire life, and have been disappointed time after time. I was thrilled when the Constellation Program was announced, but not surprised when it was woefully underfunded. When the cost of Constellation started to rise during an economic meltdown, it was canceled, and replaced with a mission to visit a small orbiting rock, which was also canceled. I have absolute faith in politicians to put political considerations ahead of what is best for humanity long term. And what is best for humanity long term? It is impossible to know with absolute certainty, which is why humanity does best when there are multiple options. When a few common sense guidelines are enforced, and people have the freedom to choose for themselves. And that brings us back to Elon Musk. How is he different from the United Launch Alliance, or Jeff Bezos? One difference is that ULA is not trying to reduce the cost of space development. It is trying to maximize its profits, which is fine and even necessary for a publicly held company. But most of us want more, a higher goal. Jeff Bezos has shown that he was also a fan of space exploration since at least high school, with dreams of orbital habitats called O'Neill cylinders. Bezos also wants to land on the moon, but what's stopping him? He has built the Blue Moon lander. This lander was planned to fly on the New Glenn, and uses a BE-3U hydrogen-fueled engine to land up to 4,500 kilograms on the moon. The problem is that despite not having launched anything to orbit, and being the sometimes richest man on Earth, he wants to be paid up front with taxpayer dollars before he will try to make this work, offering to offset some of this cost only when denied the contract. Elon, on the other hand, is willing to bet his personal fortune on a greater good. There is absolutely no doubt that Elon could spend the rest of his life in extreme luxury if he chose. He does not have to sleep on factory floors or fly all over the country. He does these things because he has a dream. That dream is not to be the richest man on Earth. He's done that. His dream is to give the human race the opportunity to explore the solar system. While Elon may not be sympathetic to every individual, he appears to be sympathetic to humanity itself. He sees that in our short-sighted approach to life, we are introducing ourselves to what is the most likely candidate for a great filter. With all those star systems and planets that we can see with our instruments, why don't we see more evidence for other civilizations in space? We aren't sure yet, but it is possible that species don't adapt their thinking from faster, more primitive emotion-based systems, necessary for their early survival, to slower, more considered reason-based systems, critical to their future. Many argue that Starship is not as good for deep space missions as SLS would be, and they are right. SLS can send a large probe straight to Jupiter. Starship cannot. Starship is made to lift mass to low Earth orbit. Though a 100-ton probe released from a Starship in low Earth orbit could get about 4,500 kilograms to Jupiter in the same time frame. SpaceX is not the only way possible. And while Elon has accomplished a lot, we should never assume that he is right about everything. We can't even be positive that Starship will work. But we can be positive that it is Elon's goal to make it work. And that, because of hard work, talent, and luck, he has the resources to maybe see it through. Elon is not some divine savior. He is a terribly flawed person, as I've said, just like the rest of us. But he is dedicated to this vision of humanity, expanding its civilization into space. And right now, he is our best hope to see that in our lifetimes. If something should stop Elon or SpaceX, the rest of us must be prepared to carry on. Speaking of flaws, several astute scholars said they thought I got the thrust of the solid rocket boosters for the Shuttle and SLS wrong. And they were right. A lot of things in the U.S. space industry are still done in Imperial. I don't agree with this. Metric is better in almost every way, and having a planet-wide system for science and engineering makes sense to me. The article I was going by was discussing the difference between the shuttle boosters and the SLS. It listed the total thrust as 40 meganewtons. I assumed that was the thrust of the boosters only. That was my mistake. Here is the graphic I was using. You can clearly see that this is with boosters. That means you must subtract the 7,440 kilonewtons of thrust that the 4 RS-25 engines produce from this total. The thrust of an individual SLS booster is also given in this article as 3.6 million pounds of force. If they had quoted this in newtons, as they had done here, or if I was more used to using Imperial, this mistake would have been obvious. If we put the number given into a converter, to avoid errors of course, we get a little more than 16,000 kilonewtons, or 16 meganewtons. Exactly as these astute scholars said, switching from metric to Imperial is a bad idea. In fact, it destroyed the Mars Climate Orbiter. The U.S. spent $125 million on this mission. The Jet Propulsion Laboratory used the metric system for orbital calculations, but Lockheed Martin used Imperial in the design and construction. Thruster data was reported in pounds of force, while the program was expecting newtons. This took the orbiter 100 kilometers off course, causing it to dip too low into the Martian atmosphere. The mistake we made wasn't nearly as expensive. It doesn't change our calculations because we weren't using their boosters anyway. And this was a thought experiment. Thought experiments are all we can afford right now. We would, of course, have a team double-checking things if we were actually going to build something. The purpose of these thought experiments is to introduce ourselves to concepts so we can discuss them and learn from each other, not to actually advocate for every design we discuss. I would not actually advocate that we build this design for several reasons. One of them is that the core stage itself is not designed to withstand this type of launch. The boosters have a lot of axial strength. The core stage does not. The core stage is actually somewhat suspended between the solid rocket boosters, which is why it can be so light. These boosters help support its mass when the core is filled with propellant. By the time the boosters separate, the core has burned through a lot of propellant and has a lower mass. Let's look at how this works. The boosters lift from up here, as well as supporting the core stage down here. The forward attachment point consists of a ball on the solid rocket booster and a socket on the external tank. These are held together by one bolt. The bolt contains one NSD pressure cartridge at each end. NSD stands for NASA Standard Detonator. Here you see one. These are bolts with a small explosive to sever a mechanical link. They have been used since the Gemini program, and are made by Chemring now. A link to a NASA paper on these is included in the description. The forward attachment point also carries the range safety system cross-strap wiring, connecting each SRB RSS and the external tank RSS with each other. The range safety system is somewhat similar to what we also call a flight termination system, or FTS. There was one of these termination systems on each booster and one on the external tank. A flight termination system blows a rocket apart if it goes out of control. This keeps large pieces from impacting populated areas. But you don't want to blow up a rocket with people on it if you can avoid it. The Space Shuttle originally had ejection seats, the same ones used on the SR-71 in fact. In an emergency, these could be activated up to a velocity of Mach 4, which would be the first 1/5 of flight time. There were also only 2 of them. These were active for the first glide tests of the Enterprise, and for STS-1 to STS-4, when there were only 2 crew members on Columbia. Once there were more than 2 crew members, these were disabled. The ejection seats were part of the range safety system, and here you can see the range safety system armed indicator light, in this image from inside the Columbia Space Shuttle. Solid rocket boosters had attachments to the external tank here and here. The aft attachment points consist of 3 separate struts: upper, diagonal, and lower. Each strut contains 1 bolt with an NSD pressure cartridge at each end. The upper strut also carries the umbilical interface between the SRB and the external tank and onto the orbiter. When 3 transducers in each combustion chamber reported that the pressure in these chambers had dropped below 50 pounds per square inch. I know, this is how NASA reports it. The separation sequence was initiated. There was a backup timer in case this system failed. Once the sequence started, the thrust vector control system on each booster, seen here, would set to the null position, and the main propulsion system would switch to the second stage configuration. The system would check that the thrust from the boosters was less than 100,000 pounds, as booster thrust dropped to less than 60,000 pounds. At this point, a fire command would be sent to the NSDs. The SRBs separate from the external tank within 30 milliseconds of the ordnance firing command. There are 4 booster separation motors on each end of each SRB. These are bigger versions of the solid rocket motors that you may have seen on model rockets. The BSMs separate the SRBs from the external tank. The solid rocket motors in each cluster of 4 are ignited by firing redundant NSD pressure cartridges into redundant confined detonating fuse manifolds. The separation commands issued from the orbiter by the SRB separation sequence initiate the redundant NSD pressure cartridge in each bolt and ignite the BSMs to effect a clean separation. The Space Shuttle boosters would then parachute back. The SLS boosters will not. If we really wanted to use a hydrogen-fueled core stage with a Starship booster system, how might we do it? This might be a better way. Let's do some homework. These boosters will be assumed to have a dry mass of 180 tons each. Let's add 20 tons for the nose cones and make it 200 tons each, and a propellant mass of 3,400 tons each. The core stage will have a total mass of 1,500 tons, with a propellant mass of 975 tons. How much of the residual mass could get to orbit? If we assume that we will need 9.4 kilometers per second to reach an orbital velocity of 7.8 kilometers per second. It's okay to fire the 3rd stage if you need to. How much mass could reach low lunar orbit, assuming a delta V of 4,100 meters per second, and an efficient 3rd stage using RL-10 rocket engines at 462 seconds of specific impulse? How much could land on the lunar surface, assuming a 2,000 meter per second delta V propulsive landing? And how many tons could get to low Mars orbit, assuming a delta V to low Mars orbit at 4,300 meters per second? And then how much could land on the surface of Mars, assuming a delta V from terminal velocity of 500 meters per second. Let us know your answers by email, terranspaceacademy@gmail.com, and stay safe at Astra Pro Terra.